Hello and welcome to the channel. In today's video I want to take a look at a graphics hardware feature which is widely known and used on various 8-bit platforms including the Commodore 64. But it seems to be largely unknown on the PC, and this is unusual because it's actually mentioned in the IBM documentation for EGA and VGA. But I don't find a whole pile of tutorials on how to use it on the PC. So was it widespread and just a secret of the game developers and demo writers of the day? Or is there some reason why it's not widely used? That's what I want to get to the bottom of in today's video. How widespread was this implementation in hardware on the PC? How well was it implemented? And how useful is it on that platform? This is a game called Ghosts and Goblins for the Commodore 64, and it's our starting point today because I have it on good authority that it uses a technique called Sprite Multiplexing. And that's interesting for us because it's one of the main applications of Raster Interrupts. Sprite Multiplexing is a way of getting around the hardware limitation that there are only a fixed number of hardware sprites, for example 8 on the Commodore 64. Games will typically have a fixed background and then a whole load of small images that move around, like this little man moving back and forth, that's me of course, and these zombies that I'm firing at here. All of the objects that they're carrying, the weapons that I'm firing against them, and even the little explosions are little sprites. Now these are displayed on the Commodore 64 using some sprite hardware. And of course, given that there's a limitation of 8 sprites, if you want to have a very complex game like this, where there can be often quite a lot more than 8 sprites on the screen at once, you need to have some additional tricks and techniques. Now, it wouldn't be very useful if the sprite hardware wrote the sprite information directly into the video RAM, messing up whatever the programmer had put in there. And so instead, the sprite hardware typically waits for a specific point on the screen where the sprite needs to be drawn. It waits for the electron beam to reach the precise line where that sprite needs to be displayed. And then instead of issuing data from the ordinary video RAM at that point, it issues data from the sprite itself, thereby painting the sprite in that location. But this creates an interesting possibility for the programmer. The screen can be split up into multiple regions, for example, the top of the screen and the bottom of the screen, and you can use the hardware sprites at the top of the screen and then use them again at the bottom. And this would effectively double the number of sprites that could be displayed at any given time on the screen. There are other techniques as well. For example, one can just keep a list of sprites in order of their Y coordinates, and once a sprite has been drawn, then just reuse that sprite hardware for whatever sprite is next in line to be displayed on the screen. But how does the programmer know when the sprite is finished drawing? After all, the sprites are being drawn automatically by the hardware and the programmer isn't directly in control of that. Well, what the programmer can do is keep a track of all the sprites that are currently displayed on the screen and their current positions, and then they can use the fact that the hardware provides hardware interrupts which can be fired at any given point on the screen. In particular, they'll set these so that they fire at the precise line on the screen where the sprite finishes drawing. And then the programmer knows that the sprite unit is free at that point, having just finished drawing a sprite, and they can use that sprite unit for another sprite further down the screen. This allows for a very large number of sprites to be displayed on the screen, in practice limited only by the speed that you can update those sprite units and how long it takes a sprite to be drawn. And so it's possible in games like this to display a very large number of sprites at the same time using these raster interrupts and this multiplexing technique. But what about the PC? Well, this is the IBM EGA documentation, and it talks about a vertical interrupt feature, which doesn't sound very much like raster interrupts, but it is in fact a primitive raster interrupt. Now, the vertical interrupt feature can only notify that the vertical display refresh time has ended, whatever that means, and we'll come back to that a little bit later. So this is a very primitive operation compared to what the Commodore 64 is capable of, for example, but bear in mind that PCs don't have Sprite hardware. The idea is that the EGA card can generate a signal at the same point in every frame that software can use to sync with what the hardware is doing. The way it works is it can be set up to send a signal along interrupt request line 2, IRQ2, to the CPU. And this triggers an interrupt, in this case interrupt 10 or OA in hexadecimal. And then a small software handler will do whatever needs to be done every time that interrupt fires. Now, the rest of the documentation here is pretty straightforward. It just talks about how to turn on this vertical interrupt feature, which is off by default. One just has to set bit 5 in a certain register in the EGA card. And it also talks about the necessity to check that the signal actually came from the EGA card. It turns out that from the 286 onwards, IRQ2 has a second interrupt controller attached to it, and in turn to that, a whole load of other stuff could be attached, generating interrupts. So you really have to check whether or not IRQ2 was triggered by the EGA card or by something else. But once you know that, then you can use this signal to synchronize your software. Well, the IBM documentation made this sound fairly simple to do, so I wrote a little program to test out this vertical interrupt feature. What it does is it changes the background color, color 0, to some kind of magenta when the interrupt is fired, and then waits a little time and then switches it back to black again. And this is the result. I'm running this on my IBM EGA card, which of course we know should work, and I'm using my XT clone machine, so we don't have to worry about IRQ2 being used by something else. This is not a 286 machine, so it doesn't have that second interrupt controller attached to the IRQ2 line. But those of you who watch the channel regularly know that I have a fairly large collection of EGA and VGA cards that we can try on an XT. There's a full-length Chips and Technologies EGA board. There's another one here. This is an EGA multi-res board. Then I've got a bunch of VGA cards. There's a couple of cards that do EGA and VGA, and then some other half-length EGA cards. So there's two Paradise ones here. This is also Paradise. Video 7, Trident, Genoa, ATI, Senglab's ET3000AX, and a TD3588A. So there's plenty of variety here, and we'll see which ones actually support this vertical interrupt feature. Well, the results are interesting. Most of the EGA boards do exactly the same thing as the IBM EGA card. This is one of the full-length Chips and Technologies boards, for example. And what's interesting is that there's only a little bit of background showing here, and yet there's a very long delay in my program. So the interrupt itself must be occurring way up in the vertical retrace period. But the result is not the same for all of the EGA cards. This is what happens with the Paradise EGA cards, for example. There's more background color here, which means that that interrupt must be occurring later in the frame. And this shows that there's no consistency between the way this feature is implemented between different EGA cards. The two cards with EGA and VGA output, the Trident and Video 7, behave a little differently. They do generate the interrupts. My program checks that there's 1,000 of those generated before quitting, and at 60 frames a second that's about 16 seconds worth. So the interrupts are definitely there, but there's no color on the screen. I've checked that it's not just hiding up in the vertical retrace period, for example, and I don't know why this is. Some EGA documentation says that you're not supposed to modify the palette outside of the vertical retrace period, and most EGA cards seem to support that just fine, but perhaps not these ones. After all, my program is actually doing that. The three cards with just pure VGA output behave differently again. Now, two of these are 8-bit cards. They just have an 8-bit ISA slot. One of them actually has a 16-bit slot, but works just fine as an 8-bit card. And all three of these don't generate interrupts at all, which is really bizarre because the IBM VGA documentation says exactly the same thing as the EGA documentation, that this vertical interrupt feature should exist. But yeah, my program just sits there and hangs, waiting for interrupts that never occur. Now, there's a variety of reasons why the interrupts might not be there. The chipset might just not support it. That's obviously a possibility. Another possibility is that it doesn't actually use IRQ2. Some other cards use different interrupts instead. And the other thing to check is that it's actually connected. So IRQ2 goes through the 4th pin on the back of the card, starting from the faceplate. And in this case, we can see that there actually is a trace coming from that pin. But it goes up to here. Well, that's mysterious. What's it actually connected to? Well, looky here, there's actually a jumper. And at the moment, it's off. So if I set that jumper, maybe the IRQs will start working. Well, let's give it a try and see what happens. Initially nothing, but then it pops up. It seems to use more of the screen, just like the Paradise EGA cards did, although this is an LCD monitor, so it's not apples versus apples. And also, it's a little bit short. It seems to only be about 13 seconds. Things are a bit different with the 16-bit VGA card. There is actually a trace going from the IRQ2 pin, but I don't get any interrupts. And I did try the jumpers just in case, but it made no difference. This board just doesn't support the interrupts on IRQ2. And things are very different indeed on the Paradise VGA card. You can see that the 4th pin along isn't connected at all, so there's no way that this can generate interrupts on IRQ2. As for 16-bit VGA cards, I have a lot of those, but I'd have to do some extra work. These would have to go into an AT-style machine, and if you think about it, anything connected to the 2nd interrupt controller in those machines is going to trigger an IRQ2. And so even these cards don't actually need to be directly connected to the IRQ2 line for the interrupts to work. But there's also another problem. The IBM documentation is wrong when it talks about how to tell whether the interrupt came from the EGA card, or in this case the VGA card. It turns out that that test will only tell you if something triggered an IRQ2, which is not at all helpful. And there is a way around it, but even then, there's no way to tell whether something else triggered an IRQ2 at the same time. So it's really not a particularly reliable mechanism when it comes to the AT and above. There are some interesting things online. People find chipsets that support the interrupts, but no connection to the slot, so they wire it up directly and get the cards going. But I think we're going to have to leave this for a later video. Of course, I'm interested to know whether the games use this feature. And loading on the screen at the moment is Ghosts and Goblins for the PC. This came out before VGA, so in theory it should be an EGA game, and I think there's a hint of that in the bottom right of the screen at the moment. It's very, very slow on this machine. It's taken minutes so far just loading data. And I'm using the Paradise VGA card. Now, of course, there is no Sprite hardware on the PC, so it's not going to be using the interrupt feature for that. But since we've already seen this game on the Commodore 64 anyway, I thought it'd be cool to see it on the PC. Uh-oh, this game seems to be joystick only, and the only joystick I have is my Dick Smith one from way back in the day. And yeah, it just doesn't work with a lot of games, this one included, so that's the end of that. According to a user on the Vogons forum, the game Gauntlet requires the EGA interrupts in order to function. Now, I had a little bit of trouble at first finding a version of Gauntlet that did anything at all. There's one actually that doesn't even have the Gauntlet executable that's floating around out there. But once I found one, it is an EGA game, and so let's find out whether or not this actually works on this VGA card that I have, which we know doesn't have the interrupts because the IRQ2 pin is not connected. So we'll go into the game and we'll just select one player, and then we get to choose our warrior. So let's just pick the first one there. And then the screen just goes blank and it just sits here. It's not trying to load anything. It just doesn't work. So maybe this is actually right. Let's switch over now to an EGA card that does have those interrupts and see what happens. This is the Genoa EGA card, so let's give this a try and see if it's any different. And look at that, we're actually getting something. So I'm not actually sure how to play it here, but yeah, it really does seem like it works with a genuine EGA card. Why on earth it needs interrupts just for this, I don't know, but yeah, that seems to be actually correct. My goodness. Well, I'm really surprised. I totally did not expect that at all. Looks like a fun game anyway. As a final test, I put the ET3000AX video card in. That's the one where the jumper selects whether the interrupts work or not. And let's see if it runs on this machine. Well, it does seem to do something, but I don't know if I would say that's working correctly. It looks like it's actually out of sync somehow with the screen. It's not too surprising perhaps because of the 70 Hz VGA, but at any rate, at least with the jumper on, there's something happens. Let's try taking that jumper off and see if there's any change. Well, in actual fact, not only did the screen stop flickering, but the machine stopped responding altogether. So yeah, it does really seem to need that IRQ too. So I think that confirms it. This game really uses those interrupts. Well, I think we might be in a position to summarise what we've found, or rather confirmed, since others have looked into this before me on the VCFed and Vogon's forums. Basically, it looks like if you had a real EGA card, then probably the interrupts are going to work. If it's a combined EGA-VGA card, well, they might still work, but some of the other implementation details might be slightly different. But by the time you get to real VGA cards and Super VGA cards, it looks like a mixed bag. Some will work if you set a jumper, others use a different interrupt entirely, and still others just don't support the option whatsoever. So I guess if you were in the EGA era and you're a game manufacturer, then maybe you would have used this feature, and that's why we end up with EGA games like Gauntlet that actually do rely on this interrupt. But on the other hand, it's not a particularly useful feature on the PC. It's implemented rather inconsistently, and so there aren't very many games out there that actually require it. So far, I only know of two, and that's the ones mentioned in the Vogon's forum. Maybe you're aware of others. Let me know in the comments if you are. Well, I think we have time for some viewer comments, and the first video is where we put a CGA card in a 486 machine and also repaired my IBM PC. And unfortunately during that repair, I fixed a variable capacitor but called it a variable resistor or potentiometer by mistake. So thanks to everyone who picked up on that error. It is a variable capacitor and it's used to tweak the signal coming from the system clock, which is used for everything in the PC, including the ISA slots. And so it's actually used to adjust the composite output of the CGA card. If it's not quite right, you'll get a black and white image on an NTSC monitor. If it's correct but a little bit off, then the colors won't be right. So you adjust that until everything's perfect. And of course, this was broken in my PC, and so there was all sorts of glitching going through the entire system whenever this moved. The next comment is about that mysterious T-Res chip that I found inside my floppy drive, and quite a number of people correctly said that this is a termination resistor, a little bit like SCSI drives where you have to put one on the final drive in the chain to prevent the signal from bouncing up and down the cable and messing everything up. But in the case of floppy drives, it doesn't seem to matter as much, and there were some varying opinions in the comments as to why that was. Some people suggested that the later controllers handle things better, perhaps even terminating the bus on the controller itself. Other people said it only matters if you have really long cables, and bear in mind that in the early history of IBM computers, they would have had very long cables going out to drives, perhaps even in separate cabinets entirely. And other people said, well, it's a floppy drive, it's slow, it probably doesn't matter that much. And I think some of those explanations certainly sound reasonable, but without some long cables and scientific test conditions, I'm not going to be able to give a definitive answer on why it doesn't seem to matter that much on PC floppy drives. As for a CGA card and a 486, Jim Leonard reckons I picked a bad game to benchmark. Grand Prix Circuit is frame locked to 10 frames a second, so no wonder I couldn't tell whether it was going faster or not. He reckons a better option would have been Jet 2, and goes on to say that it's actually pretty hard to find a game that would run way faster on a 486 in CGA. And this underscores the whole anachronism of the whole thing. People weren't putting CGA cards in 486s to play games back in the day. It just wasn't done. It's only something that we can do nowadays for fun. Now, Andrew Jenner had some interesting comments on the CGA benchmarks themselves. In the video, we found that 2 of the 4 ISA bus speeds that we tried in the BIOS settings gave us the same benchmark scores. And this is odd because the ISA speed should control the speed of the CGA card, which is the bottleneck. And Andrew reckons it's down to the pattern of wait states that the CGA card emits to tell the CPU not to access the bus while it's accessing its CGA memory to update the screen. But of course, those wait states that it's emitting have to be synced up with what's going on the monitor. So they don't really change as you change the speed of the ISA bus. What happens is that operations in my benchmark, such as writing into CGA memory, have to fit in between these wait states. And just speeding up the bus a little bit might not make enough difference to get an additional operation in the gap. And it's only when the bus speed gets fast enough that suddenly there's enough space to get another operation in and you'll notice a performance increase. So I think this is a very likely explanation. So thanks, Andrew, for pointing all of that out. Well, that's going to be it for this week. I had intended to add a section on repairing the hard drive in my IBM PC, but this was quite involved, so I'm actually going to leave that for a later video. Anyway, if you enjoyed this video, don't forget to like and subscribe, and we'll see you in a later video. Bye!